vorticity and magnetic fields and quantum matter. I started reading the bottom, fractional vorticity. Okay. I was going to say, that's pretty relevant, you know. Okay. No.
Now you can hear me, okay. So thanks for the presentation. Thank you, all of you, for staying alive here for the very last talk. And also, let's go back. Yes. Of course, thank you, the organizers, for this very nice conference. And thank you for giving me the opportunity to present this work, along with Professor Fabrizio Canfora. He's from Centro de Estudios Científicos in Chile. He's a professor in Centro de Estudios Científicos in Chile, and also Universidad San Sebastián. I'm a late postdoc in Universidad Austral de Chile, also in Valdivia, and also have affiliation in Charles University in Prague. So, this work, what I will present here, is divided in these two works. The first one is, it will be the core of this talk, is a recent paper in Nuclear Physics B. And this second paper is more related to the poster. It was in the poster session real on the right wall of the poster in the corner about this one particular solution on what we talk here. Here we will extend what we show in the poster. We will go to the, let's say, going deeper in the structure of the solutions we found in that paper here, in which will be appear. It's let's say, approve it, but we are waiting for the proofs. So it will appear in European Journal Physics C. Of course, we have also this archive if you want to see. So let's start with a very, very quick review of a Gross-Pitaevskii equation. The Gross-Pitaevskii equation is an equation which governs the Bose-Einstein condensation in the presence of interactions, different kinds of interactions. The most common, and we will see, is what is called SAIFR interaction. There are even more. We will see a couple of these during this talk. And what is important is that it's one of the most important system of partial differential equations, and it describes many properties, non-trivial properties of experimental features of superfluid and supersolid. But unlike for instance, the Griswold-Landau theory for superconductors, we don't have too many analytic tools to study the Gross-Pitaevskii equation as we have for Griswold-Landau theory, for instance. Therefore, for that reason, could be welcome to have some method to find analytic solution for the Gross-Pitaevskii equation. One of the solutions was presented in the poster. Here we will find another solutions for different kind of Gross-Pitaevskii equations. So this is the Gross-Pitaevskii equation, for instance, the static Gross-Pitaevskii stationary Gross-Pitaevskii equation. There is no partial derivative with respect to time, and there appear this coupling constant. Psi is the wave function which describes the Bose-Einstein condensation. It's a complex function, of course, and it can be separated in the real part, phi1, the imaginary part, phi2, or if you insist, you can write it in the amplitude phase form. Rho is the amplitude and S is the phase of the wave function. I recommend these books, of course, Pitaevskii, one of the authors of the equation, is also an author of this book, this very nice book, which is the detailed derivation of the Gross-Pitaevskii equation, Pitaevskii and Stringari, and also a newer, this is a classic book, but there's also a newer book, more brief book, but very nice, of Varengi and Parker, which is deduce also this equation from, let's say, first principles. So, one particularity is, not particularity, the energy for Gross-Pitaevskii system has this form, and this is why we call this kind of equation psi4 to the 4, because this psi to the 4 is what's appearing in the energy of the energy functional for Gross-Pitaevskii system. Gross-Pitaevskii system are systems which obeys the Gross-Pitaevskii equation, of course. This is the effective potential, sorry, effective coupling constant, which depends on h bar and this coupling and the mass, etc. But this is the form, more or less, and for us this will be enough to show about a Gross-Pitaevskii equation. Now let's go to the core of the talk. So suppose we have these two partial, this system of two first-order partial differential equations. X and Y we are in two dimensions, but I didn't say that, but we are in two dimensions. Suppose we are in two dimensions. X and Y are the coordinates of these two dimensions. And we have two real fields, phi1 and phi2. Suppose you have this equation, derivative of respect to x of phi1 plus derivative with respect to y phi2 equal to some function, in principle arbitrary function of phi1 and phi2. And we have the equation 2, which is the partial derivative with respect to y, phi1 minus partial derivative with respect to x, phi2 equals some other function of phi1 and phi2. Now, let's take equation 1. We derive the first equation with respect to x, and adding the derivation with respect to y of the second equation. This is one equation, we form one equation, and we can form another one if we subtract the derivative with respect to y, the first equation, with respect derivative of respect to x, the second equation. Okay, and what you get is something like that. Here you have, for these two equations respectively, you have the Laplacian of phi1 equals something proportional to the derivative of phi, first derivative of phi, plus something which is this third term, is proportional to the derivative with respect to phi1 of a squared plus b squared. And this analogy for the second equation, you get exactly the same for phi2. Okay? With this c1 and c2 are these two parameters. It will appear here, the derivative with respect to phi2 of a and plus derivative with respect to phi1 of b. This is c1, and c2 is derivative with respect to b of phi2 minus derivative with respect to phi2 of a. I will come back on this because it will be important for some theoretical reasons, let's say. And because A and B until now was arbitrary, we'll take C1 and C2 equal, what happens if we impose C1 and C2 equal 0? Of course, we get this because all the terms proportional to the first derivative gone, and we get these two equations. The Laplacian with respect to phi1 is proportional to the derivative with respect to phi1 of a squared plus b squared, and the same for phi2 on the second equation. So what happened? If we take something which we call it a superpotential, W, which is a function of phi1 and phi2 in this, and suggestively, we take this zeta as phi1 plus I phi2, which at the end of course is psi in the Gross-Pitaevskii equation. But let's take this notation to resemble the complex the complex functions. If A is the real part of this W and B is the imaginary part of this W, you will see that this equation, when C equals 0 and C1 equals 0 and C2 equals 0, resembles the Cauchy-Riemann conditions for an analyticity of a function of, in this case, zeta. So if we have an analytic function of zeta on the right-hand side of this equation, this is the real, remember, this is the real part of W, this is the imaginary part of W, we get something like this equation, which until now is very nice. But let's see what happens if we take particular case for W. The first particular case of W is proportional to zeta squared. If you take this k is a constant, after a moment we will see what is the meaning of k, but until now it's just a constant. We have the equation, the set of equations we started with. The left-hand side are the same, but the right-hand side, if you take zeta squared, this is the real part of this, which is now is proportional to phi1 squared minus phi2 squared, and the imaginary part is proportional to phi1 times phi2. And if you make the trick that you derive respect to x, the first ones, and some respect to y, the second, and blah, blah, you get the Gross-Pitaevskii equation for the psi to the fourth potential. So to the fourth interaction, let's say. And this is what appears in the poster. So the poster was a particular case of this. Also, for miscellaneous, if you can rewrite the energy functional for that case, and you can accommodate these fields and this A. Okay, A are functions of the fields, so you can accommodate the fields to get something like this. Something which is squared, a term which is squared plus another term is squared. So if phi1 and phi2 fulfills these equations, saturate the energy is a local minimum, let's say. So this is why we call this kind of BPS equation, the first order equation, we call it BPS equation. So have two, let's say, two consequences. First consequence, if you have a solution of the first order equation, it's a solution also the second order, in this case, this Gross-Pitaevskii, and second, it saturates this energy bound. This is the solution, which appears also in the poster, is perhaps better explained. These are the analytic solution of this function, of this system, sorry. You can check that this is an analytic solution. This is for the amplitude. You can write the fields in polar coordinates, in this case. And then you see that there appears this 1/3 term in the cosine or sine function, which means that this is what we call a fractional vorticity, because you need, in this case, 3 terms to get the same value of the equation, and this is why this kind of plots these are the plots for those solutions of phi1 and phi2. You need necessarily branch cuts. In this case, we took the branch cuts in the positive x-axis. And then you see why there is a continuity, because when go around one time, you don't get exactly the same. You need 3 times to get the same value of the function. Okay, you can play this game for other superpotential, let's say W. This is another case. For instance, zeta to the 5/2, and you get this strange BPS system, but you can solve it. This is the modified, let's say, Gross-Pitaevskii equation you obtain if some couple of fields fulfills the first order equation, it fulfills also this one, and you get this another solution with different fraction of the fraction here in the angle. In the other case, you have 1/3, here you have 2/7. And if you take the other option, the last option we will take, there are even more, but the last option is theta to the 3rd, you get this right-hand sign for this BPS, which is the first order partial equation system. You get this, and if you take the same track, you get this Gross-Pitaevskii equation with this interaction, in which in the energy becomes this. This is like psi/6. This is why we call psi/6 interaction, right? And for any function which is analytic, again in C1, in phi1 and phi2, you can reproduce this family of solutions of this family of Gross-Pitaevskii equation, or Gross-Pitaevskii modified, as you wish to call it. And in the phi to the 6th case, you get the fractional angle, let's say, is 1 to the 4th. So the pattern here is that if you use W as, for instance, zeta to the n, you can get a solution which is 1 over n plus 1. This is the pattern of the fractional vorticity that appears. And this is, again, a solution for this psi to the 6th example, okay? So let's make these final remarks that in the present work has been shown a large class of generalized Gross-Pitaevskii equation, generalized in the sense that psi/4 is the standard one. We have psi/5 or psi/6. There are also examples of multi-fields, could be done also. You can also take W as a sum of different potential, different potential of zeta. Also, there are some examples appears in the paper, in the reference I gave you in the first transparency. This formula allows to have the powerful tools of usually used in BPS, trying to find configurations for Gross-Pitaevskii, trying to use it. All the formulas appear, all the tools appear in BPS equation to Gross-Pitaevskii. This is our hope with this work. And future work is a lot of work. For instance, to interpretate what are the solutions, how will be experimental setting to obtain this solution we have with this method. This is pure mathematical methods. We still don't have. We could have candidates. We still don't have any real reproduction, real lab reproduction of some configuration of that form. It would be nice could be connect this fractional vorticity with fractional statistic, or use, for instance, something that bring fractional quantum Hall effects in supersolids. Perhaps in that case, some configurations with fractional vorticity appears, but fractional vorticity is difficult to get with manipulations, and the advantage here is that it appears almost for free, in the sense that all the solutions of this BPS system contain fractional vorticity. Okay, again, are the two papers we refer if you want to go to more details. The first one I'll show you in the first slides. So, from Moldavia, thank you, and thank you thank you the organizers also.
Okay, questions? Yep.
Nice talk.
Thanks.
Usually when we solve nonlinear differential equations, we don't have ensure that the solutions are unique, and even if they exist, how do you know that your solutions
No, we
are
don't
unique?
know. are not unique, of course. Actually, I didn't present here. We have another solution in the poster, which has different behavior. It's like a wall. We call it domain walls because you have a singularity in a line if you plot it in Cartesian coordinate instead of polar coordinate. So yes, there could be. This is one of the solutions we found. For us, it was interesting in the sense that fractional vorticity appears naturally, but there are other solutions. Yeah, and of course, that the solution, I mean, the Gross-Pitaevskii equation have many, many more solutions than that. This is just, we are saying that if psi1 and psi2 are solution of the BPS, is also solutions of Gross-Pitaevskii, but could be many solutions of Gross-Pitaevskii which are not solution of the BPS, of course.
Okay, thank you.
No problem. Thank you.
Thank you. So very nice talk.
Thanks.
Just a quick question. It seems by the technique you're using that the manifold phi1 plus I phi2, what you call capital Z, is a conformal manifold to the original Z variables, right? So in a sense, your solutions is a family of conformal solutions.
Could be,
to the
yes.
Could be.
Yes, could be the case. As you comment yesterday, yes, you can write. I didn't write here, not in the paper also, but with Fabrizio we tried something, and you can write these two equations in one equation. It's something like derivative with respect to zeta bar of psi bar equal k, or whatever you put, psi without bar squared. And there are two importance, which is this square breaks also some symmetries there. Then usually BPS breaks symmetry, so this is what happened. But yes.
Okay, any final questions? Okay, let's, no. No. Yes.
Yeah, so yeah, this is very, very interesting. So my question is that when we consider the superfluid vortex, then the angular momentum is also the quantized. So this configuration, so does this have also there some fractional the angular momentum, or?
We don't know, but there's at the final of the paper in nuclear physics bay, we, let's say, try to put some ways in which this thing could appear, and I think, I don't know if this answers your question, but multi-fields could be possible, a way to have similar configurations of that, where angular momentum different, the multi-fields of vortex and the angular momentum of vortex coupled each other, and this is a possible way to have this kind of solution. Yes.
Okay.
We still don't know. Thanks.
Okay, let's thank Pablo again.
Thank you.
And now I'll hand it on to our fearless leader for discussion.
Yeah, so this is welcome to the last discussion session. Just to sort of enhance the quality of the discussion and